let's work now on problem 12, page 320 for Siegel's biochemical calculation. Okay, so this is problem 12, number 12, and again, page is 320. And this problem states that the embryonic liver tissues contain an enzyme that catalyzes the reaction S2P, substrate to the product, and the adult liver also displays S2P activity. So the same activity was found in different tissues, and some kinetic data are shown below. What conclusion can you draw concerning the identity of two enzymes? So the table that's given gives the concentration of the substrate and the velocity of the reaction when the enzyme was used from the embryonic liver tissues, and also when the enzyme was a source of the enzyme was from the adult tissue. So it's asking for us to make a conclusion about what is this kind of enzyme, whether the same enzyme or different enzyme. So this is a very classical problem in biochemistry, and what we have to do is to find out what's the Km to compare to see if these enzymes are the same or not, or if they are different. If they are the same Km, we cannot say for sure that it's exactly the same enzyme, but if they are not the same Km, then we can assume that these are different enzymes, okay? So the table is extensive, and we already visited this problem before. When we have a situation like that, we can have an oversimplification and find a solution during an exam, for example, without having to use the computer. Let's say here, let's pick up the two first data of the substrate concentration, 1.67, 10 to the power of negative 5. And the second one was 2.5, 10 to the power of negative 5 also. So in order for us to get the double reciprocal plot, we would have to invert all this concentration here. So let's do that. For the first one, the inverse of the first concentration give us 59880. Okay. The second one, the inversion of that give us exactly 40,000. So remember, this we are going to use this thing as this is going to be in the x, right? So this is going to be the delta x, which we have here already, 19,800, 880. All right. So then we have here from the adult, the data that comes from the adult liver, the velocity was 1.05 and 1.55 for those concentration only. I'm picking up only two concentration, right? So first we are going to need later the 1 over V. So let me do that. This one is easy, 0.952, and 155, which gives 0.649. Okay, so we already have another value here that we are going to use, that the delta y. Remember, I'm going to find the slope and solve the problem the same way that we solved the first problem of this series, okay? So this difference here is 0.303. Now let's look at the embryonic data. And the velocity for the embryonic data was, for the first one was 5, and is 6.66. So let's calculate the 1 over V. This one is 0.2, and the other one is 0.15, 0.15. So the delta here would be 0.05. All right. So let's start with the adult first. Let's work on the adult first. So for the adult, the slope of that plot is going to be delta y over delta x. Delta y for the adult is 0.303. We could do mano a mano, side by side. but let's do one at a time. That's less complicated. 19,880. Okay, so what this thing give me? All right, so it gives me 1.52 10 to minus 5. Well, this is the slope of the curve. Do you know what I'm doing, right? Remember, what I'm doing is that we have a curve like this, and in order, this is going to be the 1 over v, that's your y, and this is 1 over s, that's your xc, right? And if you want to calculate the slope, we take the delta y, delta x for any interval, and it gets a good approximation for that, right? All right, so we know now that the slope is 152, so the linear equation now is y equal 152 10 to the power of negative 5, which is the slope, times x plus b. And if you plug in the values for any of this number here for the adult, then we can calculate the b, right? We have a pair of numbers. For example, if you use this one here and this pair here, then we are going to get the value for b. So let's do that. Y, in this case here, y is 1 over v. 0.952 equals 152 10 to the power of negative 5 times x. X was 59,808 plus b. So we do all this calculation here. We're going to get the value of b, which will be divided by 0.952. So the b itself is going to be 0.042. Okay, that's b. I don't want b. What I want is the km, and the value of km I find in here, km, right? So what's this thing? What do you have in that equation here? Is that 1, y is equal 0. This intersection in the x line here is going to be what you need. So I go back and redo this equation now, but using y as a 0, because I want to find out what's x when it crosses the y line at 0. So that's going to be 152 10 to the power of negative 5 times x, that's what I want to find, plus b. I know now b is going to be 0.042, right? So let's calculate this x here. So x is going to be equal 152. Okay, so minus all right, so x it gives us minus 2,763. And what's this x in here? This is the x when y equals 0. So that this x in here, that's negative 2,763. And we know that this number is an inverse. This x is inverse of km, and it's a negative also. So now I would say that km equals 1 over 2,763 divided by 2,763. All right, so that this gives us 3.6 10 to the power of negative 4. What's the unit for this? Molar, right? We are using molar concentration here. Okay, so let's repeat the same process now for the embryonic. If they become approximately the same value, then it's probably the same enzyme. If it's a different value, it's probably a different enzyme. It's most likely a different enzyme. So let's do the same exercise now for the embryonic tissue, right? Liver tissue. So the slope for this one here is going to be equal. What did you get there? The delta y was 0.05. The delta x is the same, because you use the same value for the two of them. 880. and this give us 2.52 10 to minus 6. That's the slope. The slope that we are saying that now is that y equals 2.52 10 to minus 6 x plus b. All right. Now we go back and use the values from the embryonic and plug in and get b, right? So let's do that. For example, the first one was 0.2. It was the y, and the x was 2.52 10 to minus 6 first, and the x was the same, was 59,880. Okay, plus b. So let's calculate b from here. Okay, so b is equal 0.049. 0.049. So now we do the same exercise again, because now we know that the any number can be plugged in here and it would give, because now we know the equation is 252 10 to minus 6 x plus 0.049, right? So we want again the same number. We want again the place where x is going to be, y is going to be 0, and what's the crossing x? So 0 equals 252 10 to minus 6 times x plus 0.049. So what's x out of here? $49. So that's negative 19,445. And what's this? This is minus 1 over km. Minus 1 over km. So km then is going to be equals 1 over 19,445. Invert the all right, so for this one in here, we got 5.14 10 to the negative 5 molar, quite different from the other one. So if they were very close, then we would say that experimental error, especially that we are using this approximation, but they give so far away from each other that's very likely that they are different enzymes. Okay, so the answer for that question is they are likely different. All we need to calculate is the Km. It's a little bit tedious process, but we can calculate that in an exam without need a computer to do that. Well, of course, the best way, as you showed before in other examples, the best way is to do a complete calculation and to do curve fitting to get the exact values of the result, the best approximation, okay? So that's the solution for problem 12 in Siegel's biochemical calculations.